Good morning. The topic of my presentation this morning is power transformer diagnosis and maintenance, to test or not to test. That is the question. So the question, why should we test or not test? Well, we would like to prevent this kind of occurrence in our substations. A burning transformer is something that nobody wants to see. Or here, the skeleton of a transformer. Well, it's quite obvious why we don't want this, but obviously we don't want the lost power transformer hardware, which costs millions of rands to replace. A fire like this can result in damage to secondary equipment in the substation, such as neighboring breakers, current transformers, even neighboring transformers, cabling, as well as the relay house in the near vicinity. It obviously will result in extended periods of loss of supply to the customers of a municipality, apart from the personal safety risk that is associated with a fire like this, both to substation personnel as well as fire personnel that are subjected by this. So what causes power failures like this? And there was an interesting survey done by Seagray a couple of years ago in 2015, where they surveyed worldwide about 22,000 grid transformers with a total lifetime of 150,000 years. And they categorized the reason why these grid transformers failed into all these categories that you can see on the right-hand side here. The three main areas that stand out are failures due to winding, 38%, failures due to the bushings failing, mainly the HV bushings failing, being 17%, and lastly, failures due to the tap changer. And all of these three categories, winding, bushings, and tap changes, in total, about 86% of the failures of power transformers relate to the electrical or the active part of the power transformer, which means it could be prevented, or at least it could have been predicted by suitable diagnosis and suitable testing techniques. I'd like to share a real case with you. In this picture here, you see a very typical 22 MVA transformer. In this case, it was 132 kV to 11 kV. It is situated at one of the major municipalities in this country. This transformer tripped, and it then was tested, and there was still some specific testing that needed to be done on this transformer before the municipality wanted to return this transformer to service. The municipality couldn't do that test themselves, and as a result, this transformer stood idling, meaning it wasn't supplied and couldn't supply customers for many days, resulting in a huge problem for the customers because the suburb that this transformer supplies didn't have electricity for at least 3 days. We were then called in to assist and to also showcase our test equipment. And when I stood there at the transformer, I said, this is crazy. How can this be? A transformer like this not supplying customers? The question that popped up in my mind was, what revenue is lost for such a 22 MVA transformer not supplying customers? I took some assumptions. I said, well, let's say this transformer is loaded 100% during the day. That means for 16 hours a day. It is loaded 50% during nighttime. And let's assume a rough 250 per kilowatt hours, just because it makes the numbers easy. The revenue that is lost for this transformer not supplying its customers to the municipality is 1 million rand per day. 1 million rand per day, easily calculated by using this formula, as you can see down here. That means even the capital equipment that we brought for this test could have been paid off in a single day. That is a return of investment of 1 day. I mean, this is a business case that any financial person will immediately sign, because this is amazing. So this really made me thinking and said, really, we need to change something in the way that we look at how we maintain and how we diagnose our power transformers. And this made me think of the Maimonides principle. Give a man a fish and you feed him for a day. Teach a man to fish and you feed him for a lifetime. Well, I'd like to use my author's freedom here and convert this a little bit and say, this is the Alectrix principle. Give a utility a finished test report, they can supply power for a year, maybe also only for a day or a month. Teach a utility to test themselves, they can supply power for a lifetime. And this is really the purpose of my presentation here today, is to provide you, the municipalities, with a toolbox of the tests that can be done on a power transformer, and to be able to, for you to provide power to your customers for a lifetime. I've categorized this into 3 categories. Firstly, the basic tests that need to be done or can be done on a power transformer, which is number 1, just basic visual inspection of a power transformer, looking at the transformer, recording oil leaks, looking at the silicon breathers, recording any funny noises coming from the transformers. Secondly, we've got the dissolved gas analysis, which means we take an oil sample from this transformer on a regular basis, and we plot the results from that oil analysis in the Duval triangle shown on the right-hand side here, where we plot the methane content, the ethylene content, and the acetylene content against each other. And this would indicate to us if there have been any high energy thermal faults inside the transformer. If this would indicate if our oil sample would fall into one of the T1, T2, or T3 areas on the right-hand side, those red areas shown in this diagram that you see here. Or if it's more on the left-hand side of the diagram here, it would tell us that there have been discharges of low energy inside that transformer. This is a very good diagnosis technique on a power transformer on an ongoing basis. It should be done on a transformer on a regular basis. And lastly, you can conduct an insulation resistance measurement on a power transformer by just basically measuring the power transformer with a 5 kV measure. And if you apply just the simple rule of 2 mega ohms per kV is the absolute minimum of insulation resistance that you should measure between the windings with the HV and the LV winding, as well as the windings and the tank. Then we come to the standard electrical tests. For these standard electrical tests, the transformer needs to be switched off. It is a test that can be done reasonably fast. These are the 4 tests that we are suggesting. The short circuit impedance test, also commonly referred to as the leakage reactance measurement. It basically measures on our equivalent model or our digital twin of our power transformer. It measures the, well, firstly, we need to apply obviously a short circuit on the LV side. It measures the reactances of that transformer. And that is a figure that is given on the nameplate of the power transformer. Secret Guide 445 specifies that the measured quantity should not deviate by more than 3% from the nameplate value. Secondly, we apply or we do a static winding resistance measurement on a power transformer. This is typically done in a 3-phase DC test. Why 3-phase? Because it's quicker. It's important to make sure that the transformer is properly charged up with that DC, and you need to be careful with that because it can be dangerous if you then disconnect any of the test leads, and you need to properly discharge that energy afterwards again. And then we plot we basically characterizes the resistances R1 and R2 as shown in my diagram here. And the typical test results would look something like this, where we plot the winding resistance for each tap position of that transformer. Firstly, all 3 phases should be right on top of each other because the winding resistance for each phase is identical with each other if the transformer is good. And also the test should be in a straight line and decreasing with increasing tap number. And if you have a tap reversal switch, you will see this V characteristic that you see here, where at the tap reversal point, the resistances start increasing again because we now switch the tap winding in the reverse orientation onto our main winding. Then we have the excitation current measurement that we can do on a power transformer, either at low voltage, meaning anything up to 200 volts, or at 10 kV. This typically should be done after demagnetization, particularly for the low voltage measurement, because this characterizes the core of the transformer. And it actually models the iron losses in our transformer. And here it's very important to do this after demagnetizing that core, and the test equipment typically can do this demagnetization for you as well. And then the results that you get will look something like this, where the currents measured for the outer phases of a star winding are higher than the currents measured for the center phase. The reason being because the way that the flux distributes inside a 3-limb transformer, we'll typically find that the center phase can be anything up to 40% less than the outer phases. The outer phases, because the transformer is symmetrical, should be the same. They should be virtually on top of each other. And also for increasing tap position, the excitation current should increase, because as you are increasing your tap position, you've got less winding, so you need more current to energize that transformer. That's why this current is increasing with increasing tap number. And then we have the transformer turns ratio measurement on a transformer, typically referred to also as the TTR. This is also a 3-phase test. Why a 3-phase test? Because it was just quicker. You can do all 3 phases at the same time. But the other big advantage about this 3-phase AC test is that we can energize our transformer with a balanced AC voltage. We will then not only measure the ratio measurement or the ratio measurement for each phase, but also the phase angle shift between the HV and the LV, the vector group measurement of that transformer. And we're then characterizing this ideal transformer that we see in the middle here, this ideal transformation ratio. Typical results will look like this. Again, we do this for all tap positions, and all 3 phases should obviously again be right on top of each other, because the transformer ratio should be the same for each phase. And also the measured transformation ratio should not deviate by more than 0.5% from the measured, from the nameplate data that is on this transformer. And that is an IEC 60076-1 standard that specifies this limit. And you can see here in the test results, it already shows us the plus and minus 0.5% limit. And as long as our measured deviation is within this range, our transformer can be passed and can be switched back as normal. These are the 4 standard electrical tests that we suggest for any transformer, be it a 400 kVA small little distribution transformer all the way up to a 20 or 40 MVA transmission type transformer. And these tests typically take, even for a transmission type transformer, should take you no longer than an hour to conduct. That includes even setting up, connecting the leads, as well as generating the test reports afterwards. It's really a very quick test and a very useful and a very conclusive test in terms of the health of the electrical parts of this transformer, in terms of the windings, the tap changer inside that transformer. And now we come to the advanced portion of our test toolbox, the advanced test and diagnosis methods. And this is really requiring a bit more technical expertise, as well as also experience in terms of interpreting the test results and so forth. And here we suggest 6 different tools, if I can call it that, or tests to be done on a power transformer. The first one being the dynamic winding resistance test, which is in essence also a DC test, similar to the static winding resistance test that we did earlier under the standard test. But in this case, we are measuring for a continuity between tap positions from tap 1 to tap 2, for instance. And we are wanting to ensure that our tap changer doesn't have any interruptions in the selector switches or the diverter switches from one tap to the next. It is very important that this test is done for all tap transitions, tapping up and tapping down, as well as also for all phases. And then we plot the response from those tests on top of each other. And here we can see the typical signature that we receive from a test like this. The signature meaning this is actually the DC current. And then we can see how the diverter resistors are switched in. This is the first diverter resistor, then the second diverter resistor, and then we have a discharge cycle where a certain winding is either added or switched out, and then the current discharges in that case. This process takes roughly about 200 milliseconds going through. But the transition or this fingerprint from one tap to the next is identical, or should be the same or similar for all the tap transitions, both tapping up, tapping down, as well as for the different phases. So all those transitions in a tap changer, and in this case here for a 17 tap power transformer, this is actually 96 different transitions, should all basically be able to fit on top of each other. This is a very good results that we see here, where the 96 curves are really all virtually on top of each other. The only reason why there is a bit of variation here is because at higher tap numbers, the current dips more because we've got less winding switched in our circuit. So this is very typical that what you see here. You can see here, I've actually highlighted the results for the red, yellow, and blue phase of tapping up and then tapping down. You can see they're very close to each other, very much on top of each other. And these test results really indicate a very healthy and good tap changer. The second test that should be done is the 10 delta measurement on both the winding as well as the HV bushings of a power transformer. This is also commonly referred to as the dissipation factor measurement between your high voltage winding and your low voltage measurement. And we do this also not only at a single frequency, but in a range of frequency from typically 15 Hertz up to 400 Hertz. And what we see from that is that we firstly see that at 50 Hertz, the actual dissipation or the 10 delta measurement should be, the CGRA Guide 445 again specifies less than 0.5% for a healthy transformer, or at least less than 1% is still acceptable. Above 1%, we can fail that transformer. So this measurement at 50 Hertz is firstly important, but secondly, also the shape of this curve is important because a new transformer will show us an increasing shape, meaning that the 10 delta values increase with frequency. And as the insulation deteriorates, this shape will change. And you can see here, for instance, for the ICL measurement, that this is already starting to show signs of degradation. And this will firstly obviously result in this measurement increasing, but also the shape of this curve is in another order of confidence in terms of our 10 delta measurement and our test results. Secondly, when we're looking at bushings, the same applies. We firstly look at the 50 Hertz measurement, which in this case here at 0.4% is a very healthy measurement. And again, for bushings, you cannot apply just one value. It really depends on the specific bushing that you're testing, what level you apply and not so for, and what you would fail. For oil impregnated paper bushings, again, the 0.5% limit is very much a good yardstick to use. So in this case here, we can pass this bushing without too many problems. And also we can see that these results here are still nicely increasing, which shows that the paper is still very healthy in that bushing. And also all four bushings, in this case, we had three-phase bushing and neutral bushings, were virtually identical, right on top of each other, and very good results and very comparable results in this specific case. We then come to sweep response, frequency response analysis, the SFRA. And this is a very good technique to determine the geometrical integrity of our transformer. And we might have seen these kind of signature responses that you get from a SFRA test. And this is to determine, particularly after transport as well as after heavy through faults, if the geometrical configuration of our transformer has changed. It will give us an idea of the lower frequency is where the core has changed between 2 kilohertz and 20 kilohertz. If the bulk winding has somehow changed the geometrical configuration, 20 to 200 kilohertz gives us interwinding phenomena, and above 200 kilohertz up to 2 megahertz, we can see changes in the tap change leads as well as even the test leads as well. This is a comparative measurement. So it means we want to compare this measurement against a measurement from either when it left the factory or from before it was commissioned and so forth. And this comparative measurement then gives us conclusion whether something has changed inside this transformer. So it's important to remember that this is a comparative measurement and not an absolute measurement where we have certain pass or fail criterion available. We then also have partial discharge measurements. And as the name of partial discharge measurement says, this is partial discharges. Inside our insulation medium, meaning the paper and the oil, there's always certain impurities, which causes little flashes inside those impurities, and they can be measured and can be plotted in a diagram like the phase resolved partial discharge patterns, as you can see here, in relation to the 50 Hertz test voltage applied. And each of these little dots that you see here is a little discharge that happens inside our transformer. And if the level of this partial discharge that we see here increases, that is an indicator that the discharges are increasing and obviously that the insulation is deteriorating. And this could be an early indicator that our transformer is deteriorating and the insulation is deteriorating, meaning that it could fail into the future. For this kind of test, it's very important also to be able to separate the actual discharges that are happening as a result of the discharges, of the partial discharges, from any noise that is measured around the transformer and around the environment where we're testing in. And in this case, it's very important to then have noise filtering and partial discharge separation methods available when you're doing this kind of test. And the last test to apply is a dielectric response analysis test, where we are plotting the 10 delta again. So similar to the winding 10 delta measurement, we were plotting the 10 delta of a power transformer, but over a very wide frequency range. The value at 50 Hertz here that you can see here should be very similar to the same value that we measured after 2 above, meaning 0.19% in this specific case. But in this case here, we're looking at a very wide frequency range from 0.1 millihertz up to about 5 kilohertz on the top here. The shape of the curve in the bottom here is the same as before. If it's increasing, it's good. And this whole curve shifts from the left to the right as the transformer is aging, meaning that's why we then measure a decreasing curve as this transformer ages, because you will basically see this curve sitting somewhere to the right here. And this means that the insulation is deteriorating. This then gives us the facility, this wide frequency measurement, to model the paper in the solid insulation of the transformer. In this case, it measures the paper at 1.1% of the weight of the transformer. Anything up to 2.2% as per IEC 60422, 6422, means that this transformer is dry, it's good. From 2.2% up to 3.5%, it's moderately wet. Up to 4.7%, it's wet, and above 4.7%, please don't use that transformer. Don't switch that transformer on in any way. Okay, so the last thing is we're needing to teach you to fish. And this is very important with all these test techniques, that you learn how to use these tools. And this is just a picture that was actually taken at the sponsor of our conference here at eThekwini Municipality, where we showcased our test equipment for transformer diagnosis, for testing, and to explain how to use the test equipment, how to diagnose the results, how to interpret the results. Very, very important. And this is crucial. The knowledge transfer is crucial for you to be able to not only have the fishing rod to fish, but also being able to know how to catch fish with that. So to summarize and to conclude, power transformers are of the most valuable asset in our power system. Huge revenue is lost when power transformers are not supplying power. Remember the 1 million rand per day for a 20 MVA transformer, for instance. Testing and diagnosis of the power transformers can prevent failures. There are basic diagnostics available, such as visual inspection of the transformer, dissolved gas analysis, as well as insulation resistance measurements that can be done on a regular basis on your transformers. There are standard electrical tests available, such as short circuit impedance, winding resistance or static winding resistance measurement, excitation current measurement, and transformer turns ratio measurements, which can be done on a regular basis. It should take you no longer than an hour to conduct on a typical distribution transformer. And then the advanced electrical tests available, such as the dynamic winding resistance measurement for the on-load tap changer, the winding dissipation, the winding 10 delta, the bushing 10 delta, the sweep frequency response analysis, the partial discharge measurements, as well as the dielectric response analysis on a transformer that can be used as advanced diagnosis methods to diagnose your transformer. And all of this, for all of this, is important that to be able, that you need learning to teach to fish in terms of you being able to feed for a lifetime and to be able to supply power for a lifetime. And with that, I'm at the end of my presentation, and I'd like to thank you for your attention.